Welcome everybody. Today I'll be presenting my thesis, The Application of Longline Mussel Aquaculture to Establish Subtidal Reefs, New Solutions in Coastal Defense. So Belgium, along with many other low-lying coastal nations, are at risk from coastal erosion and flooding due to climate change-caused sea level rise. Currently, Belgium spends around 23 million euros a year on coastal protection measures, including beach nourishment schemes and hard structures such as seawalls and breakwaters. However, these methods are expensive, require maintenance, and have potential negative ecological impacts. In response to this, the Coastbusters Consortium was formed in 2017 in order to seek nature-inspired solutions to stabilize the coastline of Belgium. This included two building polychaete worm reefs, marine flora fields, and bivalve reefs, specifically reefs made out of the blue mussel Mytilus edulis. Mussel reefs have the ability to inhibit coastal erosion by stabilizing sediment as well as reducing wave energy. So Coastbusters, to facilitate the formation of subtidal mussel reefs, Coastbusters is seeking to adapt a commercial aquaculture technique known as Longline aquaculture. This technique is able to recruit large numbers of mussel larvae out of the water column simply by introducing a rope substrate known as a dropper line. Due to easy availability of food, as well as beneficial environmental conditions, the mussels are able to grow to a large size rapidly. However, instead of retrieving the lines in 12 to 15 months, as is normally done in aquaculture, the lines are left in for an extended period of time. Eventually, there are one of two outcomes. One, the mussels grow to a size where the force of the current is greater than their connection to the dropper line or the surrounding mussels, and the mussels break off, usually in clumps due to their gregarious nature. Or, in outcome two, the total weight of the mussels on the line becomes too great and the line breaks, falls to the seafloor, creating a sort of mini reef where previously there was only sandy sediment. So to further investigate how effective this process is, as well as to figure out how to optimize it for future use, we came up with three main study aims. So one, does this approach actually result in a long-lasting reef? Number two, which dropper line material and structure are the best? Within this, we studied the difference between a filamentous and non-filamentous structure, as well as different dropper line materials. We studied the ability of these materials and structures to recruit mussels from the water column, and also which ones were fostering mussels that had the highest survival potential once they reached the seafloor. Finally, we studied the effect of the fouling community growing on the dropper lines. It's known in commercial aquaculture that the fouling community can have potential negative effects, and we wanted to see if this is the same in this case, especially since these lines are going to be immersed longer than the normal amount of time for commercial uses. So in March 2018, the structure observed below was placed around 2 kilometers off the coast of the southern coast of Belgium, near the town of De Pan. The structure had 48 polypropylene filamentous dropper lines suspended at around 5 meters of depth. Then, the next year, in April 2019, 10 of these dropper lines were removed and replaced with non-filamentous natural materials, as well as non-filamentous, two different types of non-filamentous artificial materials. In addition, the 2 of the polypropylene ropes were removed, cleaned completely of mussels, and placed back on to test the effects of time. Finally, in January 2020, we observed that, unfortunately, many of the dropper lines had broken off during the winter storms, including all of the non-filamentous natural materials. So in the end, we gathered 2 of the non-filamentous dropper lines from 2019, 2 of the filamentous lines from 2019, and 10 of the filamentous lines from 2018. In addition, throughout the course of the study from March 2018 to January 2020, Seven different dive surveys were conducted. Unfortunately, these surveys weren't done according to a systematic sampling protocol, but still much valuable qualitative data, especially on the growth of the mussels on the seafloor, was able to be ascertained. So in the lab, we did total counts of the mussels on 1 meter lengths of the dropper line, measured the length frequency of those mussels, as well as estimated the condition index, which is a ratio of meat to shell, which sort of can be used as a indicator of health of the mussel. In addition, we did a survey of the abundance and diversity of the macrofauna down to genre, as well as some basic statistical tests to test the effects of mussel density on the condition index, as well as a ANOVA on the effects of depth, time, and mussel density on the total number of fouling individuals. So the first question, does this approach actually create a long-lasting reef? You can see here in September of 2018, there are already mussels forming beneath the dropper line, as was indicated in outcome 1. This is 6 months after the structure was placed in the water. However, the next year, the reefs had completely disappeared. Then again, later that year, 5 months later, they reappeared in even greater number and coverage. So from these video surveys, we can conclude that a reef is formed, however, it is not able to last throughout the entire year. This is mostly likely due to hydrodynamic stress and burial from the winter storms in the North Sea, as well as heavy predation by the sea star Asterias rubens, which were observed in association with many of the mussel patches throughout the dive survey. So the next question, which dropper line material and structure are the best? For mussel recruitment, as you can see, the filamentous dropper lines indicated in blue here had a much higher total number of mussels, but in these much smaller size classes, while the non-filamentous dropper lines had a much lower total number of mussels, but at much larger size classes. So the high number and small size on the filamentous dropper lines can be linked directly to the higher surface area offered by the filamentous material. The mussel larvae are able to recruit in very high numbers on this filamentous material, but as they grow, due to the high density, they are restricted in size. This is compounded by the stronger attachment strength that mussels have to filamentous structures, so the mussels aren't able to fall off and create room for the mussels beneath to grow into these larger sizes. In addition, the filamentous material mimics natural settlement substrates such as macroalgae, which is also perhaps a reason for the high recruitment of the filamentous structures. Contrast, the non-filamentous have a much lower attachment strength to the rope substrate, so that the mussels, as they grow to a size, are able to fall off more frequently, creating the room for the mussels below to grow into these larger size classes. So this kind of leads us to the question, two materials are able to produce mussels that have a higher survival potential once they reach the seafloor. So the larger mussels are able to resist predation from sea stars, which indicates that the non-filamentous material may be creating mussels that are better able to resist this predation. However, the high density groups of mussels, seen on the filamentous dropper lines, are actually result in a much higher mussel bed stability, especially when they're firmly attached to these filamentous structures. In addition, the condition index was not affected. Was apparently not affected by even the very high density mussels in the filamentous structure. So, leads me to the conclusion that the non-filamentous material may be best used in outcome 1 when the line is consistently providing large mussels to the seafloor to be able to resist predation and allow the reef to persist over time. Whereas the filamentous dropper lines may be best in outcome 2, where they break off or even purposely cut to provide these large numbers of mussels at once, firmly attached to this filamentous structure, to be able to resist this sedimentation and hydrodynamic force that exists in the North Sea. Unfortunately, for this study, we weren't able to separate, while material certainly does have an effect on both recruitment and attachment strength of mussels, we weren't able to separate out the effects of material in the study. Finally, does the fouling community have a negative effect on the mussels? The fouling community was dominated by amphipods, specifically by the genus Yasa, which were in extremely high numbers, 1,000 or 10,000x of any other individual observed on the dropper line. However, there doesn't appear to be a current impact on the mussels within any of the parameters that we were able to measure. That being said, there does appear to be an increase in total number of individuals over time. As you can see here, the dropper lines immersed for 2 years have a higher number of individuals per half meter compared to the dropper lines immersed for 1 year. Depth did have a greater effect, accounting for around 72% of the variance in the population, but time still does have a significant effect on the number of individuals. This is confirmed by, or supported at least, by the presence of balanus in all of the samples from 2018, which were completely absent in the samples from 2019. So this may indicate that while there's no negative effect on the dropper lines at the moment, there may be a future effect as the lines are immersed in water for longer and longer and accumulates a fouling load. In addition, fouling organisms also exhibit high seasonal variation. For example, Yasa are known to increase in number in the spring and summer. So there may be a stronger effect around that time. Unfortunately, this sample was only taken in the winter in January. So suggestions for future applications of this project, I would suggest a dropper line with a lower density of filaments, still a filamentous dropper line, but with a lower density of filaments to allow these mussels to grow into a larger size, and that they're periodically cut every 1 or 2 years to create these high, these dense structures of mussels that are able to resist the forces in the North Sea. If this is the case, the lines certainly should be made out of natural or biodegradable materials and should be low cost. The filamentous dropper lines are industry ropes for aquaculture and are, as such, are quite expensive. It's also important to note that as this project scales up, we need to measure the potential. While they can provide good ecosystem services, there's also potential negative environmental impacts from basically creating a large mussel aquaculture farm off the coast of Belgium, especially near ecologically sensitive areas. So this study, we were able to come to some very kind of results and conclusions. However, the sample size overall was quite small. So future studies should increase the sample size to confirm some of these results. In addition, there should be periodic sampling throughout the year to better account for the mussel recruitment and survival, as well as the fluctuations in the fouling organisms, which should be linked to systematic sampling with quadrats on the seafloor. That'll better allow us to better able to link the dropper lines to the seafloor and really see how many mussels are being provided and how well they are surviving. Sea stars should be continuing to be monitored to see how well these larger mussel size can actually resist predation from the sea stars. And of course, since we lost all of the natural materials that would be ideal to use because of their low cost and biodegradability, there should be more research into these materials and see if they actually are effective for the use in the structure. So I just wanted to leave everybody with a more wider scale kind of multi-use, to put this project in kind of a multi-use context, where the structure is consistently feeding and creating this mussel reef below, which by creating habitat is boosting local fisheries, reducing wave energy, which in turn is helping support adjacent ecosystems such as eelgrass beds or Longline reefs. This is done by reducing the wave energy, but also reducing turbidity in the water. At the same time, this structure can provide an alternate source of income for fishermen, and reduce the amount of money that governments need to spend on beach nourishment schemes, which should lower the cost and also help protect these coastal ecosystems such as sand dunes or sandy sediment ecosystems. So I want to thank my supervisor, Alexia, as well as my co-supervisor, Thibaut, and my promoter, Hirt, who were very, very instrumental in helping me just get this all done off the ground, keep me organized. And especially want to thank the people from ILVO, David and Jan. David, who helped me count, measure, and do the condition index of over 72,000 mussels. And Jan, who really helped me identify most of the macrofauna. Thank you to my sister, who helped edit my thesis when she didn't need to, and to my Coastbusters partner, Nanu. My friends and family, of course, and IMBRSea for all of the hard work from Tim and all of the coordination office to making sure this could happen even during the crazy Corona times. So yeah, I consider this research really a product of everyone I've mentioned, and I only really make up a small part of that. So thank you all.